Okay, moving on. We want to compute the actual accumulated value and present value using delta. Okay, previously we are given accumulation function, but we want to derive the force of interest at each moment at each specific moment. Next section, we will be given the delta function, but we want to derive the accumulation value and also the present value. Okay. So, to get the accumulation function, given a delta function, it will be as follows: e to the power of the integration of all of the delta between time 0 to time t. Then you will get the accumulation function, because at is equals to a0t, right? So you are going to accumulate between time 0 to time t. Okay, we just know about this now. Later we will prove it. So if we want to look at amount function, you just times c to the same thing. For the present value, it will just be similar to 80, but you put negative here. When you put negative, it is as if you are doing something like this. You are doing at to the power of negative 1, right? So it is as if you are just taking the inverse of the 80, right? Okay, hope you understand that. So the difference between these two is just the negative. So let's now prove this relationship. Remember a lesson in calculus, you use chain rule. So if we were to differentiate ln fx, this is what we get. It will be 1 over fx times differentiate fx, right? Okay, I hope you remember the chain rule. So keeping the above in mind, keeping the chain rule in mind, we know another fact: force of interest is equals to the speed over the initial fund. So you can see this as this one can be fx, and yeah, this one at is fx. So you can also rewrite this whole thing to be d over dt ln fx based on this chain rule, right? So this is equals to d over, you are differentiating the ln at. So now we know this relationship already. Delta is equals to differentiation of ln at. So if you are going to integrate both sides, so now if you are going to integrate both sides, this side and this side, what will you get? So you integrate it between 0 and t. So you integrate here, and then you integrate here between 0 and t. Then this is what you get. And then you exponential both sides. Exponential this side. So you exponential this side and you exponential this side. So then you will get this side, you go here, and your exponential of the ln, you just simply get 80. So this is what you get. So we just proved the first relationship. Accumulated function of t is equals to exponential of the integration of delta between 0 and t. This is just to share with you the concept, but I wouldn't ask you to prove this. I just will ask you to use this relationship. Okay, accumulation value and present value with at general time. Just now, this equation is only if you start to invest at time 0 and you want to find accumulation at time t. This one is also you want to find present value at time 0. But what if you are trying to find accumulation value and present value at general time, meaning for accumulation value you start at time t1 instead of 0. So you want to find accumulation amount between time 1 and time 2, not between time 0 to time 2. Okay. Okay, now let's look at the simplest version of the accumulation function when we are using delta. So this is when the delta is constant throughout the time. So AT is following an exponential function with delta is constant throughout time. So if you do AT, usually you will have to find the integration, right? Between 0 to t. However, since this delta is constant, so if you do this integration, you will get e to the power of delta t. Okay, so let's compare this exponential function to another exponential function that we saw earlier. This accumulation function with 1 plus I to the power of t. So if you remember, this is the accumulation function that we see for the compounding interest environment where the interest is constant throughout time. So the interest is constant at I throughout time. Okay, so what's the relationship between these two accumulation functions? If this relationship hold between this I and this delta, then these two functions is exactly the same. For example, if we are talking about I of 10%, so ln 1 plus I is equals to 0.95331. So we can say e to the power of 0.9531 t is equal to 1 plus is equals to 1.1 to the power of t. Okay, these two function is exactly the same function. Okay, exercise constant delta. Let's find the equivalent I given this delta. So we know already delta is equals to ln 1 plus I. So we know delta is 0.02. So I will be exponential of 0.02 is equals to 1 plus I. And I will be exponential of 0.02 minus 1. Find accumulated value if 100 is invested at time 1. So invested at time 1, but we want to find accumulated value at time 3. So the investment is 100. So we need to find 100 times A13. So what we know is the fixed interest rate. So we do e to the power of delta t. What is t here? T is the gap between this period. So within this period, there's 2 years. So the t is 2. Okay, so you get the answer. And then what about this one? Find the present value of 100 at time 3. So the 100 is paid at time 3. So we want to find the present value at time 0 of that 100 ringgit. So you do 100 times the PVF. So the PVF is going to be e to the power of negative constant delta times the period within the time within the period, which is 3. Delta 3. Okay. Moving on, let's do an exercise where the delta function is a varying delta. So it's a function of t. So if you see here, delta is a function of t, means if you do the accumulation function, the delta maybe is lower at the beginning if you compare to the one with like constant delta. Maybe it's low at the beginning, but then okay, let's look at another example where our delta is an increasing delta. So meaning, okay, let's look at another example where our delta is a function of t, means delta changes with respect to t. So when we see here, as time goes, the delta gets higher and higher. Or if we do the accumulation function, the growth will be steeper and steeper. So some of the potential questions in this kind of with this kind of scenario is you want to find the equivalent interest rate given the varying delta. So but the interest rate between every period is different. Like this one is less steep compared to this period is more steep, right? So when you want to find the equivalent I in a varying delta environment, you need to specify which period are you talking about. So in this case, let's say you are asked to find the equivalent interest rate in the second year. So the second year is between time 1 to time 2. So how you do that is I is equals to the interest earned in that period over the beginning fund. Or another way is you can write it like this: 1 plus I to the power of 2 is equals to this is equals to A12, right? So equals to this equation. And then once you solve it, you'll get 1 plus I equals to this. So I2 will be 3.05%. Okay, so you have to bear in mind, if say you want to find the equivalent interest rate, you have to specify the period. And it doesn't mean that throughout this period, let's say now is year 2, right? So throughout this period, the I is always 3.045. No, it's not a flat interest rate. I actually changes at every moment, but on average, the interest rate I2 is actually the average interest rate over that period. It's not the actual interest rate over that period. If you want to find the actual, you have to look at the delta. Okay, next, let's recap. I suggest that you go through these questions yourself, pause this video, and then if you get stuck only, you proceed to look at the working in the remaining of this video. Okay, so which one of the following is not correct with respect to an annual effective interest rate of 10%? So the first one, is it correct? Delta is equals to this one looks very weird, but because what we know is delta is equals to ln 1 plus I. So in this case, it should be ln plus 10%. This one is wrong. What about this one? What's going on here? This is 2 times 1 plus I to the power of 0.5 minus 1. So this, I hope you recognize, this is actually 1 plus j, semi-annual j. And then you minus 1, so you end up with just j. So this whole thing is actually j. So you get I2, I upper 2 is equals to 2 times j. Is it correct? Yes. This one, delta is equals to ln 1 plus I. Correct. What about this one? D is equals to I over 1 plus I. Is it correct? Yes. Or you can also write it as IV. What about this one? What's going on here? This one, what is this part? This is 1 minus 1 over 1 plus I to the power of 0.25. Or you can write it another way. It is 1 minus V to the power of 0.25. So what is 1 minus V to the power of 0.25? Okay, I hope you remember this relationship. V is equals to 1 minus D. Okay, V is equals to 1 minus D. So, V, if we are talking about the fractional discount rate, K. Our fractional discount rate, we always call it K, right? So imagine this K is the quarterly compounded discount rate. So 1 minus K is equals to V to the power of 0.25. The discount rate have to be compatible to the period that we are talking about. So this is the period is 1 year, so that's why the D is also 1 year. But now our K is quarterly, so our discount factors also should be quarterly. So once we know this relationship, 1 minus V to the power of 0.25 is equals to K. So this whole thing is actually K. So what we got is 4 times K is D upper 4. Is it right? Yes. So all is correct except for this.